It's wonderful to see you all here. We are continuing our MRV series today. This is an area that is of extreme interest, MRV is, for all of the carbon removal industry we've seen. I will tell you that our events for the MRV series have been extremely popular, and it's all thanks to you, our audience. Today we have some excellent panelists talking about enhanced rock weathering as applied to soils, and we are going to get to that discussion shortly. A little bit about logistics for those of you who are new to our AirMiners events. We'll have our discussion for about 35 or 40 minutes, then Q&A, where we'll hear your own inquiries from the audience. We'll field some questions, and then at the end of 60 minutes, we'll stop the recording. Later on, put this up on the YouTube channel for people who want to review or who haven't gotten the chance to come to today's session. Then, after the top of the hour, we'll have a 30-minute networking session for people who want to hang around, get to know each other, and discuss the topics at hand. Don't feel like you're obligated to stay, but it'd be great if you could, so that you could get to know your fellow carbon removal innovators, your fellow AirMiners. With that, I'm going to hand the stage over to Leonard Smith, who's from Puro, who's going to take the moderating reins from me. Okay, Leonard, please.
Thanks, Jason. Thanks, everyone. I'm sure I've met quite a few people on this call as well, but I guess my role this evening is to make this information and this topic readily accessible to everyone on the call. So if something hasn't made sense that we're going through, I think feel free to come back and ask us some questions in the end and leave it in the chat, because it's very useful to get feedback as this field's evolving. Look, I'll give a little bit about myself. I'm the Vice President of Methodologies at Puro.earth. So we're solely focused on carbon removals, based here in Helsinki, Finland, and started around 4 years ago. Now, majority owned by NASDAQ. Practical reality of my role is writing recipes or methodologies for how this can actually be reliably and transparently quantified, which, as you can imagine, is really challenging. And as a part of that role, I'm managing working groups, which are project developers and scientists put together to try and make science practical. So that's a rough little bit about me and about Puro and my role for today. So if I can then throw to my other lovely panelists. Mel, you're first up in my screen. If you'd like to go next, that'd be great.
So hi everyone, my name's Mel Murphy, and I am a geochemist by training, and I've an isotope geochemist, and I historically have used non-traditional isotopes and geochemical tools such as major ion chemistry to understand water-rock interactions in both the modern environments, but also in paleo weathering environments. So I'm a recovering academic, and I joined Undo about a year ago, and I lead the research at Undo. So to tell you a little bit about what Undo do is we're a carbon removals project developer scaling enhanced weathering to offer high quality, high permanence removals, not avoidance credits, which will be sold on the voluntary carbon market. My job at Undo is to lead the research within the team, and I am working with a team of scientists to model carbon sequestration, to monitor any potential negative effects to soils or to crop health, particularly around trace metals, and also to develop techniques to verify carbon sequestration, as well as look at any potential co-benefits to soil health and crop yield. So Undo have already spread about 18,500 tonnes over 2 continents, and we're working with global aggregate and mining companies to scale globally. So I'm super excited to be here, and I'm really excited to be a part of this panel. So thanks very much for inviting me.
Thanks, Mel. Perfect. And appreciate the background for everyone if they're not familiar with you guys. It's really interesting work that they're doing. Mary, you're next on my screen. If you'd like to give an intro to everyone. Thanks.
Perfect. Thank you, Leonard. It's so good to be here with you guys today. Thanks for joining. Really excited for the conversation here. So my name is Mary. I'm a co-founder and the CEO of Lithos Carbon. Kind of like Mel mentioned, we work with basalt in farmlands, and we're working on transforming farmlands into permanent carbon removal centers. So doing storage that's for 10,000 years or longer. My background actually comes from software, scaling software very rapidly across many, many different countries and markets. But I decided I want to spend the rest of my life working on the climate problem, because kind of like a lot of you folks here, I thought it was the most important problem that our generation has to tackle. So I went back to school. I studied geology and earth and planetary sciences at Yale University, which is where I met one of my co-founders. Our research at Lithos Carbon is based off of about a decade of work and MRV studies, honestly, at Yale and at Georgia Tech, to figure out how we can safely, reliably, and rigorously scale carbon removal through enhanced weathering, and also make sure that there's a lot of trust in the field. So I spent some of my time in school doing hydrology modeling, a little less geochemistry than folks here, but also spent some time on that as well. And I'm really excited to chat with you guys about how MRV scales, how we're approaching the market. For a bit about Lithos, we do basalt in farmlands. We're mostly focused in the States right now, but we have some projects overseas as well. We are just 7 months old, so we're young in terms of the company, and we've spread about 11,000 tons of rock this year, and are scaling up fast with farmers. So really stoked to chat with you guys today and prepare those questions. We're here for it.
Thanks, Mary. Nice, lively as always. Appreciate it. Frank, tough act to follow. You're up next. Thanks, mate.
Absolutely. So thanks, Leonard, and thanks everybody for joining the call. My name is Frank McDermott. I'm Professor of Geochemistry at the University College Dublin. I've been working on low temperature geochemistry for a couple of decades now, I guess, and particularly interested in the carbonate system, which of course is relevant to this, what we're doing at the moment. So for the past 18 months, I've been collaborating with a company called Silicate, which is an Irish company founded by Maurice Bryson about 18 months ago. And I'm the scientific lead with that company at the moment, although I'm still working in University College Dublin. So our collaboration then involves basically field trials using crushed returned concrete. So Silicate's a little bit different in that sense. We're using returned concrete. This is not in new construction demolition waste. It's actually original concrete that's been returned to concrete manufacturers. And we've been using this material on a couple of field trials, one small trial, 1 hectare, and more recently a large 125 hectare field trial, where we spread about 1,000 tons of this material in the last few months. So we're still sort of monitoring the impact of that on capturing CO2. So that's me. Thanks.
Thanks, Frank. And we have quite a bit to get through today. So, and I think everybody really wants to hear from our 3 panelists much more than they want to hear from me, but I'll try and set the scene and give you some a practical overview before we dig into some of the finer details. So I guess just to start off, what are we actually talking about in practical terms? We're talking about crushing, grinding, and spreading rock over soil to sequester carbon when it interacts with water. That's the basic principle of what we're doing as that rock dissolves. There's much more to it than that, but to keep things simple, that's what we're looking at. So when we're talking about MRV, measurement, reporting, and verification to figure out how much carbon is actually being sequestered, there's things that are easier to measure and things that are very difficult to measure in this regard. It's rather easy to measure how much rock has actually been spread. It's rather easy to do a geochemical assay on the rock to work out the type of rock that's been spread. It's rather easy to take a soil sample and work out some baseline measurements of what was there beforehand. But as we moved into the best approach for actually validating through time what's occurring, based on theory, we could have various approaches which will be unpacked today. None of these, in my perspective, are better than the other. We need to find out with time, but we could be measuring for things like total alkalinity, pH, so electrical conductivity, concentration of cations, isotope ratios, soil inorganic carbon, or total inorganic carbon. None of those are necessarily the right or wrong approach, but that just gives you a flavour for the suite that we could choose from for this. I think also relevant to give everyone a little bit of feedback in the carbon removal space. There are obviously, I don't know how many people are approaching this problem or this discussion today. So ERW or enhanced rock weathering is one of many approaches. I guess if you wanted to have a really good look and a good overview of this work globally, you could go to XPRIZE and have a look at some of the things that they're supporting. But there's many different things like ocean liming, direct air capture, many trade-offs. Some's very expensive, some's energy intensive. But I think this approach, if done safely, and we can unpack what that means a little bit later in the meeting, but if this is done safely and reliably and transparently, it has the ability to scale enormously, and also has many associated co-benefits with agriculture. I think without further ado there, I might bring Mary into this discussion to maybe give some thoughts around scalability and the economics of measuring, reporting, and verification from Lithos's perspective. And then I can bounce to Mel and Frank as we go forward, given that they're approaching things differently. But Mary, if you'd like to just join in and give your perspective on things there, that'd be great.
For sure. So I think one thing we want to do here today is, instead of doing like a little presentation from each of us, I think we want this to be a conversation. So I'm going to kick it off with some questions actually for Mel and for Frank, and also obviously I'll chip in from my end as well, about how we think about scalability, because there's a lot of different approaches. To frame this, I think the thing we all are on the same page about and need to sort of align on in this entire room of 120 folks is that, scale is really what matters here. Enhanced weathering is so cost effective, so scalable, but it does not matter if we only capture, let's say, 50,000 tons. That kind of doesn't do all that much for the planet. It's going to help some farmers, but it doesn't, solve the climate crisis. We need to get to megaton and billion ton scales, right? So the question here is, how do we develop an MRV framework for this kind of open system in a way that allows us to have trust and rigor and credibility in the field? We don't want, fundamentally, we really don't want a situation like we see sometimes with forestry or with soil organic carbon, where things have been so uncertain that, they are losing credibility, and they also have promise as well, right? But they are losing credibility over time because things have been too simulation based or projections have been too high, right? So how do we really approach this as enhanced weathering as a nascent space? Would love to hear from Mel and Frank on how you guys are thinking about scalability, economics, trust, and rigor. And then I can also chip in from my side to sort of frame that as well. Anyone can kick it off. Mel, do you want to take a shot?
Yeah, great. So I think the key thing around MRV is that we do know that the enhanced weathering system is very dependent upon some variables. And in particular, these are things like climate, pH, soil characteristics. It's also things like the basalt rock type itself, the mineralogy, etc. And so I think in order to scale MRV, what we really need to do is have an understanding of how enhanced weathering works in all of these different conditions. And so I think what's really important is that we do work together as a collaborative team to address this problem. And so what I'm really excited about the enhanced weathering community is that there is a general sense that we're all pulling together in the same direction to solve this. And so for an example, we are participating in an intermodal calibration exercise. And in fact, Lithos, you guys are also participating. So we're the two kind of industrial partners that are part of this collaboration, but it's also it's a mixture of other academic partners. And what we're doing is taking the same model inputs, putting them through our individual weathering models, which may or may not be coupled to climate models. They might be one-dimensional reactive transport models, and then looking at the outputs and comparing them to field data. And I think it's exercises like this that allows us to really understand better the sort of the limitations or perhaps the benefits of this technique under different climates, under different soil, under different cropping and planting systems. And this is what is desperately needed for us to be able to scale.
Awesome.
And Mel, just quickly to ask you a quick question that I think is positive. I mean, would you like to just also briefly discuss the associated permanence with this technique, which I think is also one of the big benefits?
Do we want to maybe throw to Frank quickly on this and then do permanence in a minute? Because I think
Sure.
Yeah, I think we have that just set up as the next one. But quickly to underline and double click on some of the stuff that Mel said there for the rest of the audience, I think that's a key thing. So to separate it out, there's sort of empirical aspects of things and simulation-based or predictive aspects. So going back to our main framing question on scalability and economics, I'm going to just toss it out there that at 10 billion tons of capture, we're probably not going to sample every single one of those billion tons of enhanced weathering capture, right? Like, I think we can probably be on the same page there. So along those lines, if we say that deep in the future, we're going to need some sort of simulation that allows us to carefully predict and very accurately predict what this will look like at scale, like, you know, a few years out. That means today we need to be generating really, really good data. Because just like Mel said, you know, on our side as well at Lithos, we see that in 2 different fields in the same climate zone, like same precipitation, same soil type, you know, a few hundred years ago, same ground temperature and all these things, same rock type that we give them. In our real trials, we see that we get completely different weathering rates in these 2 fields. And so that poses a question, right? The simulation will give you kind of similar things if you don't actually calibrate this in real world settings. So I think that with all the questions we addressed today, there's going to be a question of stages. Early on, when we're very nascent, we want to develop the best models possible. And that really comes down to the quality of the data that you're generating, right? Coming from a software background myself, I know that sort of data is everything. You make what you measure. So it's very important early on for us to generate really good data so that we can better understand how this works in diverse systems and settings down the road. So I'll get a little bit more into cost afterwards. I'm going to toss it over to Frank to talk about his approach on scalability and where we are in the field. And then I'll take the reins back for a last quick thought there.
Okay, thanks, Mary. My internet connection is a little bit unstable at the moment, so hopefully it'll be okay. So I guess one of the things that strikes me is that, as you mentioned, Mary, we did very different weathering rates in the same area, even in the same field, and so on. So I think we're still at the stage where we need lots of data.
Maybe just try without the video, Frank. It might work a lot better. We've just lost you for a moment, so we'll just pause. So things don't get too disjointed. Just try again, mate. These things happen.
Can you hear me now?
Yeah, we can hear you now. Yeah.
Okay, good. So I guess just to agree with what Mary said about the need for, I guess, more measurements in order to understand, how we're going to.
Yikes. While Frank is offline, I think he's probably trying to talk about measurements on sort of a field by field basis. I've chatted with Frank on different calls before, and I think that's where he was going. Not sure if we should move on. So sorry, Frank. What do you think, Jason or Leonard? Should we keep moving on in case Frank is not able?
Yeah, I think we can keep moving on, Mary. You said you wanted just something.
Cool. So maybe trying to sort of recap what I think Frank was going to go for is that these parameters matter a lot. So just sort of pulling that back into the system we were talking about. If you have a simulation like the ones that Mel and Lithos and the rest of us are training, if you tweak one parameter, you get an order of magnitude difference in weathering. You literally tweak surface area, you tweak one soil condition, you tweak a climatological thing. It might tell you've got twice or 3 times more capture, right? So along those lines, super important to train it up early on. And along the lines of MRV, I think Mel, Frank, and myself will start talking in specific detail about our methods of doing this. But one of the things to think about is costs. There's significantly different costs for all these different methods. Some folks have lysimeters, which are little machines. Some folks are doing things with water. Some folks are doing things with soil. All these have different costs associated with them. And I think an interesting question for us all to bounce around is how accurate, how precise are these? And also, how does the cost curve for any of these particular MRV methods change over time and reach different potential at different scales? So I think that might be a good bridge into the second part, which is accuracy, uncertainty, and unknowns, Leonard, but we'll let you and Mel start that conversation.
No, I agree. My question, though, to you all broadly would be, and I don't know if Frank's back online, but to be a little bit more specific to the group about, it's great to have data, but what is it that you actually are measuring? I think that would also be useful. I mean, you have a practical project, Mary, so does Mel, so does Frank. I think that would help everybody in the audience to actually understand this a little bit further, so that we can then actually tease some of this out. So, I mean, happy for you to start. Mel, if you would like. Frank, are you there or not? Okay, so maybe to you, Mel, if you'd like to actually give, if we're talking about accuracy, please speak to what it is that's actually being measured in the first place. I think that would help a lot. We can continue the dialogue around there.
Sure. So as Mary mentioned, it's really important that we recognize that there are multiple ways to come at this problem. And Leonard, you introduced this nicely by saying that there are different approaches, whether you're using major ion concentrations, whether you're using isotope-based approaches. We're investigating really a multi-proxy approach. We think that given the uncertainty that is inherent around this technology, from understanding what is happening in lab conditions, which are in perfect lab conditions, 25 degrees Celsius in nice clean lab beakers. The intermediate phase is looking at them in pot trials or in soil lysimeter or mesocosm trials, and then looking at the wild west that is the field. We don't think that any one particular phase, particularly in the soil system, which is inherently so complex, is going to give us that answer. So we're actually looking at it from a multi-pronged approach. So we're doing a combination of doing our own mesocosm studies, where we're going to be basically doing that intermediary stage from the pure lab phase sort of experiments to slightly more controlled stages, to also our own field trials, which have been conducted underway. And we're proposing to do these field trials in our regions of interest in which we're operating in commercially, because we know that we need to better understand how climate, how the soil type, texture, pH, various other parameters control this, and with basalt rock that's local to the region. So we're proposing to be doing this sort of study in each of our regions of interest that we're working in. And we're looking at very different phases within that soil system, soil water system. So we're looking at pore waters, we're looking at physical soil samples, we've got sensors installed in our sites. We're also doing agronomic trials, which are slightly separate to that, but they're also coupled to the same system. So we're also looking at cation movement up into plants and also heavy metals, which potentially could be toxic. So we're looking at a range of these things. And I'm sure Mary's going to talk in a minute about mobile cation to titanium approaches. So we're also looking into that because we do recognize that there are other approaches such as these weathering proxies. We're also investigating collaborations around using other isotope techniques. So one example is that we recognize that the role of strong acids is particularly important. And so for those who maybe aren't so familiar with this, but strong acids are other acids than carbonic acid that can weather the rock preferentially. And so an example of that would be nitric acid, which could be forming from nitrogen-based fertilizers. It could also be sulfuric acid, which can also form from the dissolution of pyrite minerals or other sulfide minerals present within the soil or perhaps even within the basalt. So these strong acids can actually preferentially attack the rock. And so what we recognize is that we're not only looking for alkalinity from the dissolution of CO2 in the atmosphere or CO2 from respiration from soils and root exudates. We're also looking for other acids, organic acids, all of this. So I think we're really looking into a very multi-proxy approach because, as we say, we don't really know what's going to work in each of the settings.
Great question. I think Frank might not be with us, so I'll just go from there, Mel. So likewise, we are also exploring a lot of different approaches, and we've been doing this for the last decade in our academic SURF studies. So there's the water-based approaches, which Mel also spoke about, so I'm not going to talk too much about that. One of the questions we do have with the water-based approaches, I come from a farming family. One of my co-founders also comes from a farming family. So sometimes farmers, like at large scales, they're a little bit sus about you taking water. So that's something, Mel's thumbs up. Like that's something that we're all sort of encountering. So in addition to sort of doing those kind of alkalinity studies and looking at waters, on our team, we really focus on a soil-based approach, which is a mass balance approach. So I'm not going to get into too much in the weeds, but people are really stoked to ask questions, so then I can. But we use an isotope tracer spike cocktail, a very specific kind of method that actually comes a lot from biotechnology and allows us to have very, very low error. And we do this on a range of different elements in the basalt and in the background soil. So this includes titanium, but we also do this on other elements as well. And this tells us key things about how much basalt has weathered in the field. And that gives us a very good upper bound on how much carbon can actually have been captured. And not only do we do this in the fields where we've applied the basalt, we also do this on control strips and also control fields where the basalt was not applied, but it's the same soil, the same farmer, same crop. And so that allows us to have a control that allows us to understand, what is the additional new impact that we are making on the CO2 that we are capturing on a field by field basis. So that's kind of our approach to things. When we do this isotope approach, we're able to get error on individual soil samples down to, in some cases, 0.5%. So the error is very, very low and gives us a very good reading, a physical mass balance reading of how much carbon is not just captured in a snapshot. I used to study hydrology. Hydrology is complex, lots of things go into a system, but not just a snapshot, but actually the last 7 months since we deployed, or the last 5 months, or whatever it is. So it's cool because it's an integrated look, and that sort of provides an upper bound on how much weathering could have actually happened that's additional in this field, again, compared to something that has no basalt in it. I know that was a little technical. Let us know if you've got questions. In addition to doing the initial field trials, one of the things that we should talk about is also how you think about spatial error and spatial uncertainty. So if you think about it, whether it's a water-based approach or whether it's a soil-based approach, if you take one sample for every 100 acres, that doesn't really cover it, right? So you can have 0.5% error, but one sample for 100 acres. Again, that means there's spatial uncertainty. So that's an area of increasing study for us. We're going to go ahead and publish some studies on how densely you need to sample to capture the variability even within fields. And obviously at billion-ton scale, we're not going to sample that densely. I think Calvin asked the question about how to scale, how does cost scale over time? Great question. That's absolutely critical to being practical in the field. In the early stages, we can definitely through research grants and also through, just our own funding, make sure that we're testing very densely so we have the most rigorous sort of approach to understanding how much variability we get and how many soil samples on minimum you're going to need to take in order to have acceptable error, which we report for any of our carbon credits. We report the specific error bar. So those are some quick things I want to add on to what Mel was saying. And I think we'll address this, when Frank comes back potentially, but there's also a question
Yes.
of leakage.
Indeed, Frank is right here actually.
Frank is back.
So
Okay.
Frank, what are your thoughts?
Great.
Yeah. So maybe I just comment on some of what Mary's points. I think the solid phase approach is interesting, but I think we're liable to mislead ourselves if we rely totally on that, because it doesn't tell us really what's doing the weathering. So it doesn't tell us if it's carbonic acid or nitric acid or sulfuric acid or organic acids or different kinds of acids. So I think it's useful, but as Mary said, it's definitely an upper limit on what might have weathered, because we don't really know what's doing the weathering. And I think we need to be careful about using precisions on measurements as indicators of overall uncertainty in the system. The system is very complex, and we just simply could be seduced by tiny errors on measurements, but actually there's a huge number of uncertainties that are out there, very complex systems. So I think it's really a combination of careful measurements of everything, waters, solids, a lot, and then trying to do a mass balance, at least on a plot scale, to make sure everything kind of adds up, so you can account for everything you've seen in terms of changes in the water, changes in the soil, etc. So it's only then can you have some confidence that actually you understand the system, it seems to me. And then the models, I think, need to be calibrated and tested against those kinds of measurements. And I think for me, the key thing eventually would be to try to get models that are portable, in the sense that you can employ them in many different locations. And we're still at the point really of not really understanding which measurements we need to take in the field to make these models more portable. In other words, what are the parameters we should be measuring to parameterize our models for specific field settings, and indeed for ultimately for all field settings. So I think there's some way to go yet in terms of quantification of what we're doing.
Yeah, absolutely, Frank, and thanks for your balancing insights. I think that's also really important. Yeah, I'll throw to you in 1 second, Mel. I think just for everybody else in the audience as well, some of you are very familiar with what we're doing. Some of you may not be so familiar with what we're doing, but please keep in mind that these processes naturally are very, very slow, and we're looking to enhance them. But these aren't things that are going to then just be happening in a matter of days, so that even if we're collecting data, it doesn't necessarily mean that we're able to prove anything. It takes time. We have to be patient with it, but we do need to get things started in the field so that we can start to collect that data. But this can be things that happen in months, years, decades. So just keep those time scales also in your mind as we're talking through all of this stuff, so that you actually have a sense of reality, and it's not like we're trying to prove something in a vacuum that actually can't be proven in the short term. Okay, Mel, across to you.
I actually wanted to ask Frank something about uncertainty around the weathering rates that we're using. And so I know you and I've had discussions previously about this. I just wanted to get your thoughts on that.
Yeah, I mean, I think it's very striking when you look at the weathering rates. The laboratory weathering rates are 3 to 4 orders of magnitude faster than field-based measuring rates for, say, basalt. And that's based on my own work on basalt originally a few years ago, and also more recent work that's been published on basalt weathering in the field. And the reasons for that, we think, is, basically laboratory experiments are optimized for weathering. So, minerals are effectively floating around in reactors in very acidic, often very acidic conditions where there's perfect contact between the fluid and the mineral. And of course, in the real world, in the natural world, we have minerals that get coated by secondary minerals, secondary phases. We have changes in the surface area with time that sometimes are working in the direction that we wouldn't like to see, because we get secondary minerals, including pore space and that sort of thing. So, and there's also, the biology is also obviously important in the soils, really important in the soils, which are not, all those processes are not captured in simple batch or flow through reactors in the lab. So right. I think discrepancy between the laboratory rates and the field rates are really critical. And we're talking about orders of magnitude here. We're not talking about a factor of 2 or 3. We're talking about factors of hundreds of thousands.
Yeah.
So
have you read this?
How to deal with that is tricky.
Yeah, because I wanted to discuss a recent paper that's just come out that's generated quite a lot of interest in the enhanced weathering space. So this is a paper that's come out by Francis Buckingham, who is a PhD student, and the paper came out in Applied Geochemistry, and it's a super exciting paper. And it's exciting because it's a really thorough, well thought out soil mesocosm experiment where they've added basalt to this, and they've added about 100 tons per hectare, which is a very high application density in itself. But this paper has put forward really quite dramatically low carbon sequestration rates and by inference, very low weathering rates. And I think all of the points, Frank, that you had there are exactly what we're talking to. And I think this is one of the things that we need to recognize within the community, is that we're having studies that are coming out that call into question some of these field weathering rates, and exactly one of the challenges is to marry between some of the classical lab rates, which are often fundamentally underpinning some of the geochemical weathering models that we're using to calculate carbon sequestration, but yet these sorts of rates are not being included in those calculations. And so I just wondered if you had any other further thoughts on that, Frank.
Yeah, I mean, I think we should err on the side of caution and use slow weathering rates, the kind of rates we see in the field, unless we see otherwise in the field, because after all, it's in the field we're going to be, employing the material, not in the lab. I think there's good reasons for, why we think the field rates ought to be much slower, and that's what we're seeing. And it's not just, as I say, it's not just this more recent study, but also it's earlier studies as well that are pointing in the same direction. So we need to be cognizant of that, and the fact that different soils, even for the same material, same amendment material, the same basalt, different soils will end up giving us different weathering rates depending on the pH, their organic acid content, etc., etc. A lot of it. So it seems to me we should err on the side of caution to begin with, at least, and go for these fairly kind of moderate to low field weathering rates that we see. When we actually do the experiments, and that's just based on data from both water data and for water data from mesocosm experiments, and also water data from field experiments, and indeed solid phase dissolution observations as well. So I guess my message really is that we just have to be cautious, at least at this early stage in the kind of development of this.
Right. And so I definitely agree, Frank. And I think with this particular paper, though, it's probably important to caveat that there are some limitations to this particular study. And so one, of course, is that this was a very alkaline soil. And in fact, it was pH of about 8.3, I think, was the average pH. And so they're adding highly alkaline material to this particular soil. And they had calcite concentrations in the soil ranging from about 3 to 10%. And this is because they used Oxford soils, which is already underlain by very calcareous material. And so it's not surprising to me that they saw very low weathering rates because of the combination of adding a highly alkaline material that actually contained calcite in the rock to already alkaline soils. And so I do think while we should exactly follow your advice here, Frank, I actually would like to say that some of these studies are not really representing field conditions. I think some of the other things in this particular study is they actually sieved their basalt, and what they did is they've cut off the really fine fraction, and they also didn't sample in the first portion of the soil mesocosm study. And so what that means is they've potentially not had the very fine fraction, which gives us our early weathering pulse, but they've also not sampled the first part where they may have in fact weathered some of the more sort of low-hanging fruit minerals or fractions. And so I think what we need to do as a community is just to be aware that we desperately need more field trial data where it's measured in the field, because these mesocosms and these pot trials inherently, while they're better than flow through or batch experiments, they're certainly not the panacea.
Right. And to just sort of underline that for some of the more layman audience, I think where we're going with this is that the field trials are absolutely critical. And also we need to be very aware of all the different sources of uncertainty, including the ones that Mel and Frank and over here at Lithos we've talked about, right? So to sort of put a fine point on it, one of them is the spatial uncertainty, right? You know, how densely you sample, whether it's the water stuff and how frequently you sample for the water stuff, and also for the mass balance approach. That really matters, because if you're just getting a snapshot of anything, if you're just getting one sample per large space, like that just means you've got, you know, good precision in one sample and not everything else. So that's a really critical thing to think about. The second thing is the uncertainties in the model. And so we also take a similar approach to Frank, in that we try to do as conservative an approach as possible. When we go into any of our simulations and we tweak just one parameter, like literally just tweak surface area, you can get 100 times more weathering or 100 times less, right? So that obviously doesn't work. So we try to do the empirical measurements, but that's something for folks to be very, very aware of. Like when there are simulation-based approaches and like a paper is just only focusing on that, you're going to get very variable results on an order of magnitude of difference. And then last thing is like these nonlinear patterns that Mel is talking about, absolutely critical. Like in our live field trials that I'm sure Mel has also seen as well, when you're at those higher pH ends, it's just like a very different nonlinear weathering curve. There's also in some cases a chance of a back reaction, which we have measured in different studies, not our own studies, but other fields we've done MRV for. We've seen that there are actually back reactions that we can find in the different isotope tracers that we look at, where secondary clays have been formed. You're actually releasing CO2 and you're literally not weathering the basalt. You're not capturing carbon. So of course the carbon capture rates would be low. So there's so many environmental complexities that go into the system. So it's really important for us to have these conversations very early on, to be aware that there's like a dozen different sources of uncertainty or more, and that the quality of the data and the resolution of the data we're generating are absolutely critical to establish credibility and trust on a long-term aspect in the field.
Yeah, great. Thanks, Mary. Just in the interest of time, I think we might just jump to, I guess, our last practical point that we'd also discussed internally as a group, which would be, what advice would you give to technical barrier to project developers? And then we can go to Q&A. We've got 5 minutes left, so I guess a quick couple of minutes from each of you to that point, I think would be helpful for everybody. Whoever would like to start, maybe Frank, you've been the one that's been offline the longest.
Okay, maybe just a couple of comments. So in terms of, I guess, advice to developers, it's difficult, but I think selection of soils is important. Selection of sites for amendment is important. As Mel said, you know, there's some very alkaline soils around that probably wouldn't benefit anyway from adding this kind of material, so probably not a wise choice. Equally, if we go to very acidic conditions, let's say tropical soils that are very acidic, then although the weathering rates may be very fast, much faster than in alkaline soils, we may run into problems with CO2 loss from the rivers and streams. So the bicarbonate ion may be converted back to carbonic acid, and CO2 may be degassed under those very acidic conditions. So I guess what I'm trying to say really is that there's probably some optimal optimum or sweet spot in terms of initial soil pH that we should probably be aiming for. So, you know, mapping and screening of potential sites would be from a technical point of view, at least, that would be one bit of advice to potential developers.
Yeah, I definitely agree with you, Frank. And I think the topic of reversals is a really important one. And I think the other thing that we're really concerned about is pedogenic formation. And so this particular paper by Buckingham et al., they probably did have pedogenic carbonate forming in their soil cores, but they didn't measure it. And so this just highlights the importance of measuring all of the components in your system. And this just again highlights the challenges of when you are quantifying in the field, because it is a mobile element, bicarbonate or precipitation as carbonate. How far down do you soil sample and how far do you assume that the bicarbonate has gone? And so I think these potential risks of reversibility, they're not to be underestimated. And I think this also just tells really that we do need to be working together to better understand this, because I think the biggest, the role of reversible is really one of the largest uncertainties in the field. I think the role of strong acids, I think the precipitation of pedogenic carbonate and riverine precipitation, as you mentioned, Frank, is super important. I realize that wasn't actually advice to any investors or project developers. My advice would be just simply hire a geochemist, because I think while it seems on the outward that enhanced weathering is really simple, it's really not, as you've maybe heard from some of these discussions. So that I'll leave that and throw to Mary.
Yeah, I was going to say something similar. So my two co-founders are geochemists. They're both professors. They've spent their entire lives since the time they're in their 20s doing this. And I think that this is a very interesting field, right? It's a hard tech thing. It's not, we're moving atoms, not bits. And we also have to understand these complex interactions and these second order effects that come out of these systems. Kind of like Frank mentioned with the river stuff, that's a source of uncertainty. You know, it could be as much as 10%, 20%. We don't know. We need to constrain that, right? And so as we work on building trust and credibility in this field for the long term, I think that having like a real scientific background is always helpful. Obviously, you know, if you don't have that, totally fine as well. Like there's so much other stuff that I'm sure like Mel and Frank's teams and our team are always dealing with operationally, but especially on the science side, especially in the MRV side, having a geochemical background, having an RTM or reaction transport modeling background, understanding hydrology, understanding these different aspects of the rock, these are all very important to scale, not just rigor, but also safety and credibility in the field. We want to make sure we're not damaging ecosystems. We want to make sure we're not hurting, you know, very fragile river ecosystems, for example. And that's absolutely critical. This is not a carbon solution that we should scale if we're going to cause other second order bad effects. So we need to be really diligent about that early on. But great question, Leonard.
Yeah, exactly, Mary. Thanks. And I think probably to give everyone a bit of a chuckle, back to Mel's point about, what did you say, recovering academics? I think that I've met a lot of those over the last little while, and there's a lot of wonderful folks with a lot of amazing knowledge that I think can be taken out of academia and practically applied, and giving a lot of those people, you know, field work that they can actually work on to make that more real and help us all to understand these problems better as it evolves. So, I mean, if you're finding those folks out there, give them a tap on the shoulder and give them a shot at some of these things, because practical problem solving can be very fun and very enjoyable. Maybe Jason, across to you. I think that's it from us in terms of our more formal dialogue. If we'd like to open up to some Q&A, if you'd like to just take us through that, that'd be also great. Thank you.
Sure, and thanks to the panel, thanks to you, Leonard, and our audience. Thank you for some excellent questions. We have too many questions to ask, so if we do not get to you, my apologies ahead of time. Tony, feel free to unmute and ask your question.
Well, hi, everyone. My name is Tony Ferrick. I have a quick question about the cost of these different measuring techniques that you guys mentioned in the beginning. I was just wondering if you could comment and like say which one would be like maybe the most expensive and least expensive, and then the trade-off you get with the data quality by using the different methods. Thanks.
Maybe I can start on that. So I guess it ranges from some methods that are really quite cheap, you know, like measuring electrical conductivity or pH in the field or alkalinity in the field, to other methods that are much more specialized and expensive, like isotope tracing, for example. It might be applicable in maybe only in some kind of situations, but nonetheless useful in some places. So it depends, I think, is the answer on what what we're going to kind of end up having to measure in the end. And we're still at the stage of measuring lots of things, so we understand the system better. But ultimately, hopefully, we'll end up having to measure a smaller subset of those parameters, which will bring the cost down. And maybe things like electrical conductivity, for example, in waters would be, is a good proxy for alkalinity, at least in some systems that don't have a lot of nitrate, for example, or other anions. And ultimately, we might be able to get to that kind of situation, but we're not there yet until we get more data.
Yeah, that's a great question. Chipping in here, I think it really depends on scale. So on our side, we can do things very cost effectively because we do have access to equipment. At the moment, we're also working on scaling that access out to other commercial labs to keep costs down. And then when you're working with groups where you don't own your own equipment, then the cost curve really just changes with volume, right? So in some ways, again, it just comes back to at scale, you can get these things down to very low cost, even if it's a special method. That's kind of how all laboratory testing is done today. If you think about the tests you do in your doctor's office, you're not ideally, especially in countries where you've got good healthcare, you're not paying way too much for these very high accuracy tests, right? So a lot of it comes down to scale. Obviously, the cheapest thing at billion-ton scale will be models, right? But again, we need to calibrate those better. Let's see, what are some other things? Some other things to noodle on are also where are these different tests available? And I see Jason waving us for time. So these different kinds of tests will be different in terms of, what country you're operating in, what kind of fields you're operating. One of the things we do like to do, I think across the board, is we try to hijack on existing infrastructure. So, for example, farmers soil sample a lot. That helps cut down costs. They're already going to do that. They just send us a split. So there are different creative ways that you can think about leveraging existing things that farmers already do.
Yeah.
I might just jump in on that and just sorry, quickly, and just say that also soil organic carbon, we haven't really talked about it at all. But I think what we're starting to see is that there is a deep synergy, particularly with farmers who want to be able to restore their soils and generate carbon credits from soil organic carbon. And so one of the ways in which we can reduce costs is to move towards partnership models where you're working with other providers, perhaps that are looking to couple these different techniques and do credit stacking. And what's really important, Leonard, I'm going to throw you under the bus, is that we have methodologies that allow us to certify credits. And so I'm loving working with you, obviously, in the Puro working group on our methodology. So I'm sure that in the future there will be a combined EW soil organic carbon methodology. I think the other thing too, maybe around reducing costs, is really about training our models. And so I think this is really the key thing. And so I think what's really important is the collaborative nature of the academic partners, but also the commercial partners that are participating and trying to better this understanding the science around enhanced weathering. And so I think once we have better understanding in our geochemical weathering models, I do think that we will move to a much more model-based approach. And I can actually see that David Billing is in the group here and he's been responding to a few comments. So it's actually David Billing who is organizing this inter-model calibration exercise. So I saw someone ask for the website. And so David, I'm throwing you under the bus now. And so as I said, this is just starting. So we are very soon to embark on this exercise, but it's really exciting to be participating. And I'm going to stop. Sorry, Jason.
It's all good. By the way, throwing under the bus, hopefully they're electric buses.
Okay, true.
Yes.
So
moving right along. Wes, Roberts, building on some of the topics that Mel, Mary, and Frank just mentioned, you had some questions about what does this mean for farmers? Feel free to unmute and ask.
Yeah, definitely. Maybe not totally MRV related, but I'm just curious from a farmer's perspective, does it make sense for them to go ahead and pay for the rock dust directly, just given the higher yields they'll probably experience, or do they also need the offset income to make it make sense for them?
It's a great question. I think it really depends on where you are as a farmer, because all these different rock sources are very, very different. That's like a real thing that we see live. And also they dissolve very differently in the field. So at the moment, we try to handle that for the farmer so that it's not complex. Because again, like Frank and myself were mentioning, if you literally apply something in one farmer's field and then the farmer next door, totally different results, right? So that's a little bit of a risk. Coming from a farming background myself, farmers are not down to take risks with their small businesses, which is what they run, right? So I think one of the most important things is the more data that we can generate on the agronomic benefits, and that includes the crop yield increases, that includes the nutrients we're releasing to the soil, that includes even things that we're doing studies on, including pest resistance, right? The more data we can capture on that, the better we can sort of guarantee that, or not even guarantee that, but give farmers a good sense of what to expect. At the moment, it's so nascent that it would be a little bit challenging, in my opinion, for a farmer to just roll up and buy this brand new material. I do think that at scale, that's absolutely possible though. But at the moment, we don't focus on that, and we try to be as generous to all our partners as possible, and that includes the quarries and also the farmers. So we actually do give our farmers a carbon kickback as well.
Nicholas, I see you've got your hand up. We'll get to you in a second. Bahana, you had a question as well.
Yeah, hi, Bojana here from Supercritical. Hi, Mel. One thing that I'm a little bit confused about is like how much does the particle size matter? Because to my understanding, when you talk about application rate in kilograms per hectare, like how that the particle size will really determine the total surface area, and then like how can we like how do we compare these different studies if we don't know the particle size? That's kind of my question, but there's like it relates to other things, I guess, as well.
So maybe I can just comment quickly. So particle size certainly matters a lot, and some papers will give the P80 value, the or whatever the portion less than a micron or whatever, or less than a millimeter, less than 500 microns, etc. Others don't. So it is hard to sometimes make these comparisons. But it's a kind of a trade-off, I guess, between crushing on the one hand and expending energy and therefore CO2, potentially depending on the source of the electricity and so on, versus not crushing so finely. But I think that the balance really is kind of opinion at the moment is that crushing is needed, and getting the fine particle sizes in there in that distribution of particle sizes is really important.
Is there a good rule of thumb? Is like,
sorry, can I comment on this? Because I'm like jumping out of my seat. I'm very excited. So we've been doing some modeling in the science team. And so we have some individual basalts that have been sieved down to different size fractions. We've conducted mineralogy. We've got BET surface area. And so what we've done is we put this through our geochemical weathering model. And what's super interesting is our model predictions suggest that the role of particle size really isn't playing a huge contribution on how much CDR that we can see. And so we're currently writing this up for publication. And this is in sort of agreement with some of the recent papers that have come out, particularly I think it's Arman and Hartman in 2022 in the Frontiers Journal. They certainly suggest that the role of particle size may not be as important as we may have thought, and they propose that hydrology is much more important. And that's certainly probably one of the findings that's come out of the Buckingham et al. Paper that's just been published as well. So I think we need to, this is certainly a space of active research. And I think that while our modeling needs to be calibrated with in-field data, this is something that's super exciting and I think is really at the cutting edge of research.
So I think some other interesting things there are, we find that surface area is really important. So we use a wide variety of different kinds of rock particle sizes. And, we've never used anything 500 microns. That's quite large, at least in our opinion, but we do use some larger ones. And we find that actually surface area is more important for the initial kick. So it's also the distribution. It's not just like, what most of the particle size is at. It's also the fact that if you have a long tail of stuff that's a finer particle size and that dissolves, that also kicks off like the rest of the enhanced weathering sort of process in the soils, and that also changes the base pH you're at, also changes how quickly the rest of it weathers. So one of the key things we have is in our model simulation that we use for predicting initial rates. We also have not just like a shrinking core model where we're like, oh, the particle gets smaller over time, but we also look at how the surface area changes over time, right? And that's probably a more accurate way of modeling it in a physical way. Like if you think about it and you have a particle under a microscope and it's like spiky like a star, at some point, when it weathers down, it doesn't say spiky like a star, right? And then it changes in surface area. So that's some of the stuff that we are exploring. We've also looked at, and I think a question here going to Frank's point about like, should we grind things up? Should we sieve them down? That all takes obviously some amount of energy and infrastructure. One of the things we've looked at is at least in different states in America, what's like the energy grid's contribution to this. So if you were to sieve things down or grind things down to, let's say 10 microns, which is super, super tiny, like most people don't do that, right? Like what is the break-even point for where this doesn't work anymore for your LCA? So it's all, I think, an area of nascent exploration.
Yep, great. We have time for one more question, and I promised Nicholas we'd get to him. So Nicholas, please.
I just wanted to comment on the point of West, because there are Brazilian farmers actually already paying for rock powders, and the benefits have proven here. I just here it really depends on what kind of point of view you take from a soil fertility or soil restoration standpoint or carbon sequestration standpoint, because When we're talking about application rates, I think Lisa, as you guys apply something like 30 to 40 tons per acre, and
Never applied that much per acre ever.
then per hectare, and these farmers do apply something like 3 tons per year, sometimes every 3 years. So the dosage is a lot lower than what we would aim for in carbon sequestration. And maybe check out our latest blog post in this regard, just commenting on this.
Yeah, in terms of typical rates, we do on our end, we go anywhere. We're very flexible. We just do what's best for the farmer, but sometimes it's as low as 4, sometimes it's gone up to 20, but it's always very different on a field by field basis. We've never gone up to 30 tons per acre. But yes, great point on Nicholas's side. In different sort of regions across the world, depending on their soil types and the availability of this rock, folks do actually pay for this. And there are actually some organic farmers in America that already pay for tiny little amounts of basalt as a fertilizer input, but not at the scales that we need for enhanced rock weathering to work as a carbon removal solution.
All right.
There's an
All right. Go ahead, Frank, please.
in the comments about this in terms of additionality, and if we're going to do it anyway for other reasons, then that generates questions about additionality from the point of view of generating carbon credits. So something else to think about, just to address Nicholas's point.
I do think though, sorry, Nick. I was just going to say though, while that is true, that there is a precedence to determine additionality, particularly if we use soil organic carbon as a reference point. What we do see though is that there is a certain amount of aerial extent that needs to be using a land management practice for it to be considered. Like it needs to be a common practice for it to be no longer considered additional. And so I don't know the amount of rock that's being spread in Brazil, Nick, and maybe you can comment to that. But I don't think it's not rolled out universally across the board. So potentially it would still, if we use soil organic carbon as a template, I think it probably still would be considered additional. Yeah. I don't know, Nick, what do you think about that?
It's a very interesting point. I think that's another point that would be interesting to open. What about soil organic carbon? What about the other fertilizer reductions that we have? How do we wrap all this up and put it into the carbon credit? We kind of think at the moment we really should focus on resolving the carbon sequestration, the removal part from the rock powder before thinking about the other things. However, it's sometimes hard to separate. So yeah, let's have another session looking in this, what we can all include into our enhanced weathering carbon credits.
Yeah, actually, we had a soil organic carbon MRV event just a few weeks ago, which I shared, which I have recording of on our AirMiners event recording archive. So I just shared a link to that. We're pretty much at the end of our time. So just want to say once again, thank you to our audience. You really made this event special. Thank you, Mary, Mel, Frank, and Leonard for a fantastic conversation. Too many questions to get to. That's why I shared the panelist emails in the chat, as well as a post-event survey to let us know how we did, what we did well, what we didn't do so well, how we can improve, because that's the only way we can make these events even more insightful for you and useful for us to get our carbon removal industry off the ground and in flight. So thanks so much. I also shared an event link for our next one, which is MRV on ocean alkalinity enhancement. So happy to say, by the way, we have, of the 12 Launchpad teams in our current batch, at least three of them are actively pursuing MRV. By the way, Nicholas is also in our Launchpad batch, so thank you, Nicholas, for coming. So yeah, MRV is a hot topic. We're going to continue on. Next one is MRV for ocean alkalinity enhancement. Look forward to seeing you then. Feel free to stay for our post-event networking, and we will, if not, then no worries. We will see you next time. Thanks, everyone, and have a great day.